Today we are going to cover L'Hopital's rule, which is really a rule that we can use to evaluate certain limits. Okay, and sometimes these are limits that we wouldn't be able to evaluate otherwise. Okay, but the only limits that these apply to are ones that fall into a specific form. Okay, so for one, when we use L'Hopital's rule, we'll be thinking about taking the limit of a quotient, so a function over another function. And it has to be the case that the limit in the numerator is plus or minus infinity, while the limit in the denominator is also plus or minus infinity. And so it's okay if these alternate. It's okay if one of these is positive infinity while the other one's negative infinity. And the other option we have is if both of these limits are 0. If this happens, we'll be able to use L'Hopital's rule, but we call these cases indeterminate forms. Okay, and I want to explain why. So here we actually have each example. So this one here, you can see that it's of the form infinity over infinity, right? The limit in the top would be growing without bounds, same with the one in the denominator. And you can say the same thing about all these. All these take this form, don't they? These ones on the left. Okay. They all have the same form, but all these limits are going to be equal to something else. And that, again, that's why we're calling this indeterminate. Okay, because knowing that the numerator and denominator are both growing without bound doesn't tell us a whole lot. Okay, let's see that what I've just said here is true. Well, this limit here really just becomes the limit as x approaches infinity of just x, and this is infinite. Okay. And this one here becomes the limit as x approaches infinity of 1, and that limit is just 1. And this one is the limit as x approaches infinity of 1 over x, which is 0. So again, knowing that this was of the form infinity over infinity was pretty useless because all these limits go to very different things. Okay. And we can see the same thing over here if we're in the form 0 over 0. Okay. You can see all these ones in the left are of the form 0 over 0 because now we're taking the limit as x approaches 0. Okay. But similarly, you could think about this as the limit as x approaches 0 of x, which is 0. Okay. Or this one here would be the limit as x approaches 0 of 1. Well, that's just 1. And then here I made this a right-hand limit so that I could actually say that the limit was infinity or minus infinity. But the point is it's hard to determine what this limit's going to be just based on the fact that it's of the form 0 over 0. Okay, that's really the point here. And so if we were looking at this right-hand limit, if you were to look at the graph of 1 over x, is what you would notice is that as we approach 0 from the right, this thing's going to grow without bound. Okay. All right. Let's see exactly what L'Hopital's rule is. Okay. So suppose, actually, I want to write one more thing up above. We'll come back down to this. So I already used this notation a little bit, but if we're in the case I here, the way that we'll notate this, because honestly, there's not a good notation for this. We're just going to notate it like this. And actually, I'll write plus or minus since it could be either. And if it's of this form 0 over 0, this is how we'll write it. And so is what I will tell you here in a little bit is I want you to actually write this every time you use L'Hopital's rule. We need to know that it's in one of these forms before we apply it. So here's L'Hopital's rule. And if our limit, again, happens to be of the form 0 over 0 or plus or minus infinity over plus or minus infinity, then the question is, then what? Let's see. Then the limit as x approaches a of f of x all over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. So it ends up that if you just take the derivative of the numerator and denominator, you can take the limit of that instead. Okay. But you can only do that if the limit we're working with is of one of these two forms here. And the last little note here is that this rule still applies if a is replaced with, and let's fill in a few things. It could be replaced with a right-hand limit, left-hand limit, infinity, or minus infinity. We are on to our first example here. And so you can see that this limit here does take one of those forms above. If you were to take the limit of the numerator, that would be approaching infinity. And same thing for the denominator. And so what this means is that we can use L'Hopital's rule. And you don't have to write this part, but I'm going to write it every time I use L'Hopital's rule so you all are aware of what step was it used. I'm going to just write a little LH here above the equal sign. But I do want to see this. I do want you to write down that you see that it's of the right form before you move on to the next step. All right, now if we took the derivative of the numerator, that would just be 1, and then the derivative of the denominator, that's just e to the x. And so now it's easy to see that, hey, this numerator is going to stay as 1, while the denominator is going to grow without bound. And so what that tells us is that this is going to approach 0, because that denominator is going to continue getting larger and larger and larger and larger and larger, which will make 1 over this smaller and smaller and smaller and smaller as x grows. Part B. Let's go ahead and see if this is in a form where we can use L'Hopital's rule. You can actually already see that the denominator is going to go to 0. The big question is will the numerator as well? Well, if you let x go to 0, then this becomes the natural log of 1, which is 0. If you let x go to 0 here, we get 0. And same within this last spot, we'll get 0. So if you add a bunch of zeros together, you get 0. So this is of one of those indeterminate forms that allow us to use L'Hopital's rule. Let's do that. Let's go ahead and take our first derivative. So this is the limit as x goes to 0 from the right. And I said let's take our first derivative, but I want to be a little bit careful about how I word that. When we use L'Hopital's rule, right, we're taking the derivative of the numerator and denominator separately. We're not going to be using the quotient rule here. So if we take the derivative of the natural log of 1 minus x, well, that's going to look like 1 over 1 minus x. And then the derivative of the inside is actually minus 1. So I'll just tack on a negative here. then plus the derivative of x, which is 1, plus the derivative of 1/2 x squared, which is just going to be x. And then all over the derivative of x cubed, which is 3x squared. And I'm going to do, actually before I do this, one more thing. I want to say we're actually in the same form, right? This 1 over 1 minus x. If you let x go to 0, that's 1, but then there's this negative sign here. So this is going to go to -1, and then we have a +1. Let me make sure that that looks like it's in the numerator. -1, +1, plus 0. So the numerator is just going to 0, and then we can see that the denominator is as well. So we're going to apply L'Hopital's rule again. But before we do that, let me rewrite this a little bit. How about -1 minus x to the -1? It'll be easier to differentiate if it looks like that. So this is equal to the limit as x approaches 0 from the right. And if we take our derivative, right, we're going to have to bring this -1 down, which will cancel with this one. But then when we apply the chain rule, right, the derivative of the inside, we'll have another negative. So this becomes -1 minus x, and then I don't want to forget to lower the power. And then the derivative of 1 is 0, and the derivative of x is 1. So we have this all over this times 6x. And again, you can see that we have a problem. The denominator is going to 0 still. And we do have an option. You can try and use algebra right now, but as what you'll see is even if you do a little bit of algebra, it will still be of this form, 0 over 0. So to fix this, we're going to apply L'Hopital's rule one last time. Okay, one last time. And how do I know this is one last time? Our denominator is no longer going to have an x in it. Okay. And I should be specific here too. It won't have that x in it anymore. Okay. But let's see here. If we take our derivative again, we'll have to bring down that -2. So -2 times -1 is +2. But then because the derivative of the inside, we have a third negative. So this becomes -2 times 1 minus x to the -3. Okay. And then the derivative of 1 is just 0, and the derivative of 6x is just 6. And let me make sure to write in my my limit here. So I haven't taken the limit yet. There we go. Now, it might be helpful to actually rewrite this a little bit, right? The -2 over 6 could be simplified to -1/3, and this 1 minus x to the -3, we could rewrite that using a positive exponent by bringing that to the denominator. So this becomes the limit as x approaches 0 from the right of -1 over 3 times 1 minus x cubed. So if you let x go to 0 here, this is just -1 all over 3 times 1 minus 0 cubed. So that's 1 cubed. So this is just -1/3.